Hello everyone. I am glad to present our work MLPHand, Real-Time Multi-View 3D Hand Reconstruction via MLP Modeling on ECCV 2024. Compared with monocular hand reconstruction methods, multi-view hand reconstruction is a more accurate idea, since it could leverage the geometry information offered from multi-view images. However, existing multi-view hand reconstruction methods are struggling with inference speed, which is much important in practice usage. To meet this gap, we propose MLPHand method, aiming to achieving real-time inference in multi-view hand reconstruction task, while maintaining accuracy. Our core idea comes from recent progresses in hand modeling, which implicit modeling methods become popular in hand modeling tasks, such as Hand Avatar in CVPR 2023, Lisa in CVPR 2022, and Halo in 3DV 2021. These methods usually are coordinate network, which utilize simple MLP to learn shape and radiance implicit function. Despite these implicit models are not efficient to adopt in hand reconstruction task, they still demonstrate the 3D expressiveness of simple MLP. This insights motivates us to explore a MLP-based hand modeling method, which utilizes MLP to directly regress hand meshes, such to accelerate multi-view hand reconstruction pipeline. Our contributions are threefold. First, our MLPHand operates at a speed of 71 fps on a 3090 GPU, enabled by a 75% reduction in parameters and a 90% decrease in computational complexity compared to existing state-of-the-art methods. Second, we propose two pivotal designs: 1, the lightweight skeleton 2 mesh model; 2, the multi-view geometry feature fusion prediction (MGFP) module to ensure the model's efficiency and effectiveness. Finally, we conduct extensive experiments to demonstrate that our method achieves state-of-the-art performance in terms of running time, while maintaining competitive performance in reconstruction accuracy. We now introduce MLPHand's pipeline. Given multi-view images, we first obtain a reference skeleton and multi-view visual features via a multi-view hand skeleton estimator. The multi-view visual features will be aligned with the reference skeleton to obtain skeleton-aligned geometry features, which will be fed with reference skeleton to downstream multi-view geometry feature fusion prediction module to regress vertices of hand meshes. The MGFP module consists of skeleton 2 mesh model and a controlnet-like branch, termed as multi-view feature infuser. In multi-view hand skeleton estimator, we use shared CNN to regress the heat map representation of 2D skeletons, then use soft argmax operation to obtain pixel representation of 2D skeletons. Finally, we obtain 3D skeleton via direct linear transforms method. The skeleton 2 mesh adopts per bone reconstruction strategy and triaxis modeling strategy. The former strategy decomposes non-convex hand geometry into 20 convex meshes, and represent them in parameter-sharing manner, where the decomposition way and defined order of bones is shown in Figure 2. The later strategy utilizes 3 parallel coordinate network modeling motion pattern of XYZ. Figure 3 shows the architecture of skeleton 2 mesh model. This consists of order encoding module and offset regression module. The former module converts the skeleton to 20 bone-relevant feature vectors, and the later module converts these vectors to meshes. The order encoding module aims to achieve our per-bone reconstruction in a parameter-sharing manner. Specifically, for the KTH bone, the order encoding module firstly concatenates the 3D coordinates of parent and child points of KTH bone as bone vector containing spatial information, then concatenates the bone vector B_K, the order 1 hot code O_K, and a learnable global geometry descriptor G as the final encoding vector of KTH bone. These vectors contain spatial information, order information, such to help network distinguish them. The downstream module is offset regression module. This module contains 3 parallel 3-layer MLP to regress the regress coordinates of offset corresponding the midpoint of bones. To align the visual feature with reference skeleton, as shown in Figure 4, we first reproject the 3D keypoint in each pixel space, then utilize the grid sampling operation to obtain 2D keypoint relevant features. These features will be concatenated as 3D keypoint level features. Finally, we concatenate keypoint level features like the order encoding way to obtain bone level geometry visual feature. In the MGFP module, the reference skeleton X is fed into skeleton 2 mesh model, and bone level visual features are fed into multi-view feature infuser to obtain condition refinement vectors, which will be added in skeleton 2 mesh model to output final vertices. To achieve better performance, we adopt 2-stage training strategy. In the first stage, we train the skeleton 2 mesh model only. In the second stage, we freeze the skeleton 2 mesh model and train other part. Table point 1 reports the quantitative results of evaluations on OCLinkMV, DexYCBMV, and HO3DMV dataset. The results show that MLPHand has comparable accuracy compared with SOTA method, while has best inference speed, lowest parameters, and computational complexity. In Table 2, we conduct ablation study of MGFP module. The results show that MLP module leverage visual information to successfully improve the accuracy. Figure 7 demonstrates the effectiveness of our GSD idea. We believe that the MLPHand also has the potential to insight the articulation modeling and body reconstruction. Thanks for watching.